All right, this review is about linear regression as covered in chapters 7 through 9 in Bach, Fellman, DeVoe. So we'll start out with, just the general ideas of scatter plots. The explanatory variable is the variable that goes on the x-axis. X, EX, can help you remember XX goes on the x-axis. And the response variable goes on the y-axis. Now you may remember from our chapter on experimenting that the explanatory variable is the one that you purposely manipulate, and the response variable is the one that you're measuring to see how it responded to whatever you were doing. Sometimes that's kind of an arbitrary distinction, but sometimes it's very clear which one needs to be x and which one needs to be y. Don't forget labels of your axes and a title of your graph and scale. If you are asked to ever make a scatter plot on the AP exam, if you don't have those, you're going to lose big points. The only time you would not need to have labels and scale is if you are doing a scatter plot to check a condition. Now, stat plot, first option is where you can go on your calculator to make a scatter plot, which I'll show you in just a minute. When you make a scatter plot, you use the acronym DUS for describing the distribution. So direction, unusual points, shape, and scatter. Direction should say it's either a positive slope or a negative slope or no slope, if it's completely flat. Any unusual points, outliers, or influential points. Shape, is it straight or is it curved? And scatter, weak, moderate, strong, or some version of those. Okay, so if we want to make a scatter plot, of course you need data in lists, and of course the lists have to be the same length. You have to have the same number of data points because these are ordered X, Y, right? And so then you can go into your stat plot and turn it on, and the very first one is the scatter plot. And then make sure the right lists that you are interested in are selected, and then zoom 9. Okay, so here's the scatter plot of the data from list 1 and list 2. So direction, positive. Yeah, it's going uphill to the right. Any unusual points? Well, this is kind of following the general trend of all the other points, but it is a little bit far away. So it's unusual, but probably not influential so much. If I took it out, am I going to see a big difference? Not necessarily. All right, shape. This is definitely not straight. This is curved. And scatter. Not very much scatter going on here. If we were to draw a curve through here, most of the points are going to be pretty close to that curve. And so we would say that the strength is pretty strong. Okay? Now, correlation measures the strength of linear association between two variables. So this is a word that people use in everyday speech in a different way, but as a statistician, you can't just say these two variables are correlated unless you're specifically talking about strength of linear association. If you just want to say the two things are related or associated, then you say that they're related or they're associated. To calculate correlation by hand, we use the letter R to represent it. It's the sum of the product of the z-scores divided by n minus 1. So you take every single x value, find the z-score for all of those, take every single y value, found the z-score for all of those, and then for each point, take the z-score of the x times the z-score of the y, sum all of those up, and divide by n minus 1. Now, normally you're going to use your calculator or computer output to tell you what correlation is. Now, R is always between -1 and 1 inclusive. Negative R means that the scatter plot has a negative direction. Positive R means that the scatter plot has a positive direction. If R is close to 0, that indicates a weaker association, and R near 1 or -1 indicates a stronger association. If R is exactly 1 or -1, that means the data are exactly linear. Correlation is affected a lot by outliers, so always look at the scatter plot and residual plot to make sure a linear model makes sense, which it did not appear to for the particular scatter plot that I just showed you. Now, when you do linear regression and make the line of best fit, when you're writing down your model, use a hat over the y variable to indicate it is a model's prediction versus an actual data value. Use words for the y and x variables. So we would say like height hat equals some number, whatever the slope is, times weight maybe that's our x variable, plus b, whatever the y-intercept is. Now, statisticians may use b1 instead of m for the slope, and b0 instead of b for the y-intercept. And your calculator uses b for slope and a for the y-intercept. Okay. To find a predicted y, plug x into the equation and find y. So we want to know what the model predicts for someone, with a weight of 130 pounds, plug 130 in for x, and see what you get out for y. Now, extrapolation, or using your model to make predictions for x's far from the x's used to make the model, is likely to lead to inaccurate or worthless predictions. So beware of extrapolation. Now, more on linear regression. The residual, there is a residual for every single point in your data set, right? So that is the difference between the actual y value in your data set, okay, for that given x, minus the y value that the model predicts for a given x. So if we go back to this equation for a minute, so let's say one point in your table is 140, 64. Okay, so your model is you plug, that's what a data point in your table. But when you plug 140 into the equation, you don't get 64 out for y. You get, let's say, 68 for y. Okay, so there's a difference between what the model is predicting and an actual data point in your set, and that difference is the residual. And so we would take actual y value, 60, what did I say it was, 64, and then the model predicted 68, so that's a residual of -4. So the actual value is 4 below what the model predicts. Now, a positive residual means that the model underestimates, and the negative residual means that the model overestimates for that particular x value. Okay. Now, least squares regression is a procedure to get the line of best fit, and it minimizes the sum of the squares of all of these residuals. In other words, it just makes sure that the line is positioned in such a way that all of the residuals are as small as they can possibly be. Okay. Now, in your calculator, you do linreg L1, L2, Y1. If you want to see the line, you need to do the Y1. And make sure that diagnostics are turned on to get R and R squared. So let's go do that right now. Even though this is not really appropriate for a linear model, we'll just do it to see it. So diagnostics on, you should not have to do every time. You go down to the catalog, and then if I press D, it'll get me down to the D's faster. And then I'm going to scroll down and find diagnostics on. Whoop, went past it. There we go. Hit enter, enter. And you shouldn't have to do that again unless you change batteries or something like that. And so now to do the linear regression, I go to calc. Now there are two, median. Median is a type of linear regression that we don't use in AP Stats, but that is a linear model, different way of doing it. So don't use that one, median. But if you notice here, we have number 4 is a linear regression and number 8 are linear regressions. They do exactly the same thing. It just orders the variables, just changes what's A and what's B. So it doesn't matter which one you use. Okay, so I'm going to do linreg L1, L2, vars, oh, I forgot the comma. Oh well, I'll fix that in a minute. Function Y1. Now I needed a comma here, so I'm going to go back and go second, insert, comma. There we go. Hit enter. Okay, so here is the linear regression. If you don't have diagnostics turned on, you're not going to see this R and R squared. And so it's telling us that whatever Y variable is, so let's say it's, I don't know what it is, money. So dollars, predicted dollars, hat, equals 0.82 times, I don't know, let's say it's pigs. 0.82 pigs plus negative 1.69. So there's your equation. You always have to do a little bit of rounding if you're writing it down on paper because that's a lot of decimals to write. And this is your correlation. So this is a relatively strong correlation. It's not super strong, right? And this R squared we'll talk about in a little bit. Now over here you can see the graph and the table that go with it as well. If we want to see the graph on the large screen, I'll just go zoom 9 and you can see it there. And so we could see that's not fitting it too terribly, right? Looks okay. And then this is just if you need some data. So zoom 9, you can see the graph with the line of best fit through it. When you did that Y1, it put it right here. There's your equation. You just have to scroll over to see it all. And then second graph is where you can see that table if you want. Okay, so that's how you do that. Now, when doing linear regression, always check the scatter plot, DUS, to make sure shape is basically straight, and also check residuals plot for any patterns. Oh, we have not checked the residuals plot, so let's do that. Now, every time you do a linear regression, your calculator creates a list called resid. And so I need to change my Y list to this resid list, which is stored under second stat somewhere down here. It might not always be number 7. And now every time you do a linear regression, there we go, it overwrites this list. So make sure that it's what you want and not one from a previous regression. Okay, so this line I don't necessarily want here. That's this one, so I'm going to shut that off for a minute. Okay, go back and graph. And so this resid plot is definitely not appropriate. What we want to see is a resid plot that has no pattern to it. There's roughly the same amount of points above and below. But see, this almost looks quadratic. Okay, right? There's a big check mark or something. So this would be a confirmation that a linear model is not appropriate. Okay. Now, if you need, for some reason, several resid lists, you can, I could go into, let's say, L3 and go up to the name of the list, and I can go second stat. I can put the residual list in there, there we go. Sometimes this button is behind me. There we go. And hit enter. Okay, so there's all the residuals for each individual point, which is kind of interesting. So you can tell that this one, was way above what the model predicted, and then there's the other ones that are below. And notice that there is a pattern to these. Like the first ones were all positive, and then these ones are all negative, and then we're getting to all positive ones again. So that's what we were seeing in our residual plot, that there's a pattern to the residuals. Okay. If you find standard deviation of residuals, 1 var stats would work. It represents the approximate size of a typical prediction. That should say error. Let me change that. That's funny. Typical prediction error. In other words, how far off the model will be typically for a given x. So if I go to stat, calc, 1 var stats, resid, or I could do L3 because I just put it there. Oh, it doesn't want to do that. So let me try. Clear. Maybe it'll let me do it with L3. There you go. So 1.74. So a typical residual is about 1.74. Typical prediction error. All right. Now, if you have stats instead of data, so they didn't give you data to put in your calculator, then you would have mean and standard deviation of x and y. And so then you would use these formulas to calculate the line of best fit. So your slope would be r times the standard deviation of y divided by the standard deviation of x. And your y-intercept would be the mean y value minus the slope times the mean x value. If you want to switch explanatory and response variables, you can use these equations with reversed x and y, means and standard deviations to find the new model. So make your s sub y be your s sub x and vice versa, and make your mean y be your mean x, and you can get a new predictive equation to predict the other variable instead of the one that you started out with. Okay. Now, r squared, I said I was going to talk about in a minute. Here it is. This is the phrase that you should use for interpreting r squared, which is called the coefficient of determination. So blank percent of the variation in y is accounted for by the regression line of y on x in context. So here is a computer output of r squared, 95.9. So 95.9% of the variation in height is accounted for by the regression line of height on weight, or something like that. And then that would be how you would interpret that. Outliers are points that are far from other points. Outliers that are far away in the y direction but not the x direction have large residuals and may artificially raise r. Outliers that are far away in the x direction pull the regression line toward them and may artificially lower r. These are called influential points. Consider removing influential points before regression and considering them separately. Also consider alternative models, such as curved models, if appropriate. Do not assume large R means a linear model is the best model for the data, or that it implies a cause-effect relationship between the variables. So if you're careful about all of these things, then you should, and you check your DUS and do all the things we talked about, you should be good to go with the basics of linear regression. So that concludes our review of chapters 7 through 9.